Good morning, everyone, and welcome. I'm pleased to have you here today. Today's presentation is on principles and applications of air samplers in clean rooms. We'll explore how air sampling works, why it's important, and the various applications in maintaining sterile environments. So, let's get started and dive into this interesting topic together. In this slide, we're focusing on the key objectives of environmental monitoring. First, it's about detecting both viable and non-viable contamination, meaning we want to identify living microorganisms as well as inert particles that could compromise our environment. Next, we need to verify the classification of our clean rooms, ensuring they meet the required standards for cleanliness and control. Maintaining product quality and sterility assurance is also a core goal. By monitoring effectively, we help prevent contamination that could impact product safety. And of course, compliance with GMP and ISO standards is essential to meet regulatory requirements and ensure consistent quality across our operations. Moving on, we'll look at the regulatory references that guide our practices. ISO 14644, EU GMP Annex 1, USP 1116, and FDA aseptic guidance. These documents set the benchmarks for our environmental monitoring programs. Now, let's define what environmental monitoring really is. It's a systematic assessment of our clean room conditions, regular, thorough checks to make sure that our controlled environments stay within the necessary microbiological and regulatory standards. By doing this, we ensure that the environment remains safe and suitable for manufacturing, protecting both product integrity and patient safety. Throughout this presentation, keep in mind that effective environmental monitoring is the backbone of maintaining high-quality, compliant, and sterile production environments. Let's take a closer look at why air sampling is so important in clean rooms. It's a critical part of maintaining the integrity of environments like sterile pharmaceutical manufacturing, aseptic filling operations, biotechnology labs, medical device production, and even hospital operating theaters. These are all areas where even tiny amounts of contamination can cause significant issues, so monitoring the air quality is essential. There are different types of air monitoring methods. Active air sampling, where we actively draw air through a device to collect particles, and passive air sampling, which involves simple settling plates left out to detect particles that settle by gravity. Both are valuable tools in our contamination control strategies. The benefits of air sampling are clear. It helps us detect airborne viable particles, that is, microorganisms that could cause contamination. This detection supports our contamination control strategy by providing critical data. It also verifies that our HVAC systems and HEPA filters are performing properly, ensuring the air remains clean. Additionally, regular sampling allows us to track trends in microbial contamination levels over time, helping us identify potential issues before they become serious. Ultimately, air sampling is vital because it helps us evaluate the microbiological quality of the air in our clean rooms. By doing so, we can identify contamination risks during manufacturing and take proactive steps to prevent product compromise or compromised patient safety. It's a fundamental part of maintaining the highest standards in controlled environments. Let's now look at the selection criteria for air samplers. When choosing the right device, we consider factors such as sampling volume, recovery efficiency, portability, regulatory acceptance, and ease of sterilization. These aspects help ensure that we get accurate, reliable results while also fitting the specific needs of our environment. Moving on to the types of air samplers, we have a table outlining some of the most common types, their principles, and typical uses. For example, the impaction sampler works by causing air to impact onto agar media, making it ideal for viable microbial monitoring. The impingement sampler uses air bubbles passing through a liquid medium, which is particularly useful for specialized microbiological studies. The filtration sampler, on the other hand, pulls air through a membrane filter, making it effective for capturing organisms present at low concentrations. The centrifugal sampler employs centrifugal force to deposit particles, which makes it suitable for portable clean room monitoring. And finally, the passive settle plate relies on natural sedimentation of particles, often used for routine environmental monitoring. Understanding these different types helps us select the most appropriate sampler based on our specific sampling goals and environmental conditions. Each has its unique principle and application, and choosing the right one is key to accurate microbial assessment in our cleanrooms or controlled environments. Now, let's look at some limitations of active air sampling. One key point to keep in mind is that it requires equipment calibration and ongoing maintenance to ensure accurate results. This means that the devices need to be properly set up and regularly checked to stay reliable. Moving on to the features, active air sampling is a quantitative method, which means it provides measurable data, specifically in terms of colony forming units per cubic meter, or CFU-M3. It's highly sensitive, allowing us to detect even low levels of microbial contamination, and it's widely accepted in GMP, or good manufacturing practice, facilities, so it's a trusted technique in regulated environments. Now, regarding the advantages, active air sampling offers a more accurate estimation of microbial presence compared to some other methods. It also enables faster detection, which is crucial for maintaining sterile conditions. Plus, it uses a standardized sampling volume, ensuring consistency across different samples and testing times. Let's briefly walk through the procedure. First, you calibrate the air volume to be aspirated. Then, the active air sampler draws that measured amount of air through or onto a collection medium. As airborne particles impact the media, they get captured. The media is then incubated to allow any microbes present to grow into visible colonies. Finally, these colonies are counted and reported to give a clear picture of microbial contamination levels. In summary, active air sampling is a powerful, reliable technique that uses calibrated equipment to measure airborne microbes efficiently. It's a key tool in maintaining cleanliness and safety in GMP environments, despite needing proper calibration and maintenance to keep it functioning optimally. Let's take a look at some common air sampling devices, such as the Sartorius MD8 AirScan, Merck MAS100, and bioMérieux Air Ideal. These are all examples of impaction air samplers, which work by drawing air through perforated holes so that microorganisms impact directly onto agar media plates. This direct impact method makes it easier to analyze the microbial content of the air. One of the key advantages of these samplers is their high microbial recovery efficiency, meaning they are quite effective at capturing the microorganisms present in the air. Additionally, because the microorganisms land directly onto agar plates, you can often perform incubation right there, simplifying the workflow. And counting colonies is straightforward, making these devices very user-friendly. Regarding the media, tryptic soy agar, or TSA, and saccharide dextrose agar, or SDA, are commonly used. These media support the growth of a wide range of microorganisms, which is essential for accurate monitoring. These air samplers are particularly useful in environments like pharmaceutical aseptic areas, ISO Class 5 cleanrooms, and other Grade A or B environments where maintaining strict air quality is crucial. They're also valuable for sterility testing environments, helping ensure products and processes are free from contamination. Of course, there are some limitations to keep in mind. For example, particle bounce can occur, causing some microorganisms to be counted more than once or to impact incorrectly. Also, during long sampling periods, dehydration of the agar can happen, which may affect results. Overall, impaction air samplers are powerful tools for environmental monitoring, but understanding their limitations helps us interpret the data more accurately and maintain high-quality standards. Let's take a closer look at the advantages of this method. It's particularly suitable for fragile microorganisms, which means it can gently collect delicate microbes without damaging them. This also makes it possible to recover stressed organisms, giving us the chance to study them even if they've been exposed to challenging conditions. Additionally, this technique is great for downstream analysis, allowing us to perform further tests or identification after collection. Now, moving on to the limitations. The handling process can be quite complex, requiring careful technique to ensure accurate results. There's also a risk of liquid evaporation during sampling, which can affect the concentration of microorganisms collected. Plus, this method is less common in routine GMP areas, mainly due to its handling complexity and the need for specialized equipment. For example, tools like the AGI-30 Impinger, SKC biosampler, and impingement air samplers are commonly used in this context. The collection media typically include buffered saline, nutrient broth, or sterile water. These help keep the microbes viable during collection. As for applications, this method is widely used in viral aerosol studies, research laboratories, and in monitoring high humidity environments. And how does it work? The working principle is quite straightforward. Air is bubbled through a liquid collection medium, and microorganisms are trapped in that liquid. This bubbling action effectively captures the microbes, making it a practical approach for various sampling needs. Let's take a closer look at the advantages of this filtration method. One of the key benefits is its high capture efficiency, meaning it's very effective at trapping microorganisms from the air. It's also well suited for handling large air volumes, which is important in many industrial and environmental monitoring applications. Additionally, it offers good organism recovery, ensuring that we can accurately quantify the microorganisms collected. However, there are some limitations to keep in mind. Filter clogging can occur, especially when sampling in environments with a lot of particulate matter. This means additional processing might be needed to clean or replace filters, which can add to the overall effort and cost. Now, some common examples include systems like the Sartorius MD-8 with gelatin filters, millipore filtration systems, and various air samplers designed specifically for filtration. When choosing filters, there are several types to consider: gelatin filters, polycarbonate filters, and cellulose ester filters, each suitable for different applications. Speaking of applications, this method is particularly useful in environments with low microbial concentrations, such as pharmaceutical water systems or research laboratories. It's also valuable for validation studies where precise and reliable microbial monitoring is essential. The working principle is straightforward. Air is drawn through membrane filters that trap microorganisms on their surface. This allows for easy collection and subsequent analysis of the microorganisms present in the air sample. Overall, this technique is a powerful tool in air quality monitoring, especially when combined with the right filter type and system for your specific needs. Centrifugal air samplers are an interesting and effective tool in microbial monitoring. Their working principle is quite straightforward. Air is drawn into a rotating device where the centrifugal force pushes particles outward. This causes the particles to deposit onto agar strips, which can then be cultured to identify and count microorganisms. These samplers are particularly useful in various applications. For example, they are portable, making them ideal for environmental monitoring in different locations. They're also commonly used in hospital clean areas to ensure air quality remains within safe limits. Additionally, they allow for quick microbial surveys, providing rapid insights into contamination levels. A well-known example of this type is the Reuter Centrifugal Sampler, or RCS. There's also the BioTest RCS high-flow version, which is designed for higher air volumes. Now let's talk about some advantages. These devices are compact and portable, making them easy to carry around and set up wherever needed. They also allow for rapid setup, which is crucial in time-sensitive situations. Plus, they are generally easy to operate, even for personnel who might not specialize in microbiology. However, it's important to recognize their limitations. For small particles, the recovery rate can be lower, meaning they might not capture every tiny microorganism present. Also, their air volume capacity can be limited, which might restrict their effectiveness in highly contaminated environments or when sampling large areas. Overall, centrifugal air samplers are a valuable part of our toolkit, especially when portability and quick results are priorities. They fit well into the broader theme of efficient and practical air quality monitoring methods. Let's take a look at some of the limitations of this method. First, it's a non-quantitative approach, which means it doesn't provide precise measurements of microbial levels. Instead, it depends heavily on airflow patterns, so if the airflow changes, the results might vary. Because of this, its sensitivity tends to be lower compared to more advanced methods. Now, regarding the common media used, we typically rely on TSA plates, which are tryptic soy agar plates, and SDA plates, which are Sabarod dextrose agar plates. We also use passive air sampling, where the agar plates are exposed to the environment without active air movement. The principle behind this method is fairly straightforward. Agar plates are exposed to the environment for a set period, usually between 2 to 4 hours. During this time, microbial particles settle naturally onto the plates. This allows us to capture the microbial load that's present in the air over that period. This method is often used in routine clean room monitoring, helping us ensure that environments stay within cleanliness standards. It's also useful for assessing personnel activity, seeing how human movement might influence microbial levels, and for monitoring aseptic operations, ensuring sterile conditions are maintained. One of the key advantages is that it's simple and economical. You don't need specialized equipment, just agar plates and a way to expose them. Plus, it's useful for trend analysis over time, helping us track changes and identify potential issues in the environment. Overall, while it has some limitations, this method is a practical tool for many routine monitoring activities, especially when resources are limited or quick results are needed. Let's take a closer look at the most commonly used air sampling methods in GMP environments. First up are impaction air samplers, which are widely favored due to their high ease of use and excellent GMP acceptance. They are capable of providing quantitative results, making them reliable for routine environmental monitoring. Impaction samplers also offer high recovery efficiency and are moderately priced, balancing performance and cost effectively. Next, we have passive settle plates. These are incredibly simple to use, very high ease of use, and are also suitable for routine environmental monitoring. While their recovery efficiency is lower compared to active methods, they are cost-effective and have good GMP acceptance. Now, let's compare these with impingement and filtration methods. Both impingement and filtration are capable of quantitative sampling, with impingement offering a moderate ease of use and very high recovery efficiency, though at a higher cost. Filtration provides a good balance, with moderate ease and high recovery, making it suitable for various applications but slightly more complex. Ultimately, the choice of sampler depends on your specific needs, whether you prioritize ease of use, cost, recovery efficiency, or GMP acceptance. For routine environmental monitoring in GMP settings, impaction and passive settle plates are often the go-to options. Let's take a closer look at USP 1116. This guideline provides essential direction on microbiological control and environmental monitoring practices, helping us maintain the integrity of our sterile environments. Moving on to regulatory requirements for air sampling, there are several key compliance areas we need to focus on. First, equipment calibration is critical to ensure our sampling devices are accurate and reliable. Proper qualification of sampling locations is also vital. This means verifying that we're testing in the right spots to truly represent the environment. We also need to establish alert and action limits, which serve as thresholds for when we should investigate potential issues. Alongside this, trending data and thorough documentation are essential for tracking environmental patterns over time and supporting our compliance efforts. Now, let's consider ISO 14644. This standard defines how we classify clean rooms based on airborne particle limits, ensuring our environments meet specific cleanliness levels. Then there's EU GMP Annex 1, which emphasizes the importance of air monitoring in the context of good manufacturing practices. It mandates viable air monitoring in clean rooms and calls for continuous monitoring in Grade A areas to promptly detect any contamination risks. Finally, trend analysis and investigations are highlighted as ongoing processes. They help us identify potential problems early and implement corrective actions before they impact product quality. All these points connect back to our overall goal: maintaining a controlled environment that ensures product safety and compliance. Let's dive into some important sampling considerations. First, airflow pattern plays a crucial role because it influences where airborne contaminants might settle or circulate, so understanding the airflow helps us target our sampling effectively. Personnel movement is another key factor. How people move within the clean room can impact contamination levels, so it's important to monitor it closely. Sampling frequency should be carefully planned. Too infrequent, and we might miss issues. Too frequent, and it could be inefficient. The clean room classification guides us on the acceptable levels of particulate matter, helping us determine the appropriate sampling strategy. Production activity can also influence sampling. Certain operations might generate more airborne particles, so timing our samples around these activities is essential. Now, moving on to documentation. Keeping thorough sampling records, incubation logs, and trend reports allows us to track patterns over time and identify potential issues early. Deviations and CAPA, which stands for Corrective and Preventive Actions, are critical to document because they help us address root causes and prevent recurrence. Next, let's touch on best practices for air sampling. Routine calibration of sampling equipment ensures accuracy and consistency. Using validated sampling methods guarantees reliable results. Maintaining aseptic handling during sampling is vital to avoid introducing contamination ourselves. Monitoring critical locations and intervening when necessary helps us stay on top of potential problem areas. Lastly, incubating media under validated conditions ensures that any microbial growth we observe is dependable and meaningful. All these points are interconnected. By applying these best practices, we uphold the integrity of our clean room environment and ensure product quality and safety. Let's now look at some of the common challenges and troubleshooting measures we encounter in the field. First, troubleshooting measures are essential for maintaining reliable results. Regular preventive maintenance helps us catch issues early before they impact our data. Using sterile handling techniques is crucial to prevent contamination during sampling and analysis. Ensuring correct airflow positioning helps maintain the integrity of the environment we're assessing. Proper sampler disinfection is key to avoiding cross-contamination between samples. And of course, calibration verification ensures our instruments are providing accurate and consistent measurements. Now, on to some of the technical challenges we face. One common issue is false positive contamination, which can lead us to believe there's contamination when there isn't. Agar dehydration can also be problematic, as it affects the viability of microbes and the accuracy of our tests. Low microbial recovery is another challenge. Sometimes, we just don't recover enough microbes to draw reliable conclusions. Equipment malfunction can disrupt our entire workflow, so regular checks and maintenance are vital. And operator variability reminds us that training and standard procedures are essential to keep results consistent across different personnel. Looking ahead, there are exciting emerging trends to consider. Remote monitoring systems are becoming more prevalent, allowing us to oversee environments from afar and respond swiftly to issues. Real-time viable particle counters give us immediate feedback, helping us identify problems as they happen. And the integration of automated environmental monitoring software is streamlining data collection and analysis, making our workflows more efficient and reliable. These advancements and strategies are all about ensuring the highest quality and safety standards in our work, connecting directly to the overall goal of robust environmental control and contamination prevention. Now, as we wrap up, let's talk about the conclusion. Air samplers are absolutely essential in clean room environmental monitoring. They help us maintain microbial control and ensure we stay compliant with regulations. Active air samplers, in particular, give us a quantitative assessment of microbes in the environment, providing valuable data for decision-making. Among these, impaction samplers are the most widely used in GMP clean rooms because of their reliability and effectiveness. It's also important to remember that passive monitoring plays a complementary role. While active samplers give us detailed microbial counts, passive methods help us understand contamination patterns over time. Proper selection of the right sampler type really enhances our contamination control efforts. And of course, regulatory compliance isn't just about having the right equipment. It also requires systems that are validated and calibrated regularly. All these elements work together to support a robust environmental monitoring program, helping us maintain the highest standards of cleanliness and safety in our operations. For further support, please contact us. If you have any questions or need additional information, don't hesitate to reach out. We're here to help ensure you feel confident moving forward. Thank you so much for your time and attention today. We truly appreciate your engagement and look forward to supporting you in any way we can.